Good day everyone. So for today's video, we will explain the iterative improvement method and how we use it to solve our problem and this learning task. So first, iterative improvement is a simple way of solving problems. We start with an initial or basic solution, even if it is not good yet. So we improve it step by step by making small changes. So after each change, we check if the result is better. If it is better, we keep it. And if it not, we try a different changes. So we repeat this process until no more improvements can be made. At that point, we stop and accept the solution after the final improvement. So now, this method is fast and easy to use. However, it does not always give the best possible answer. It only gives a good and acceptable solution. So, if we compare this to the other algorithms, iterative improvement is more flexible. Brute force checks all the possible answers, but it takes a lot of time. So 3D algorithm, on the other hand, is fast but cannot change its previous decisions, while iterative improvement allows us to adjust the solution as we go. So if we apply this to our problem, so our main goal first is to find compatible matches between donors and patients. So instead of solving each pair separately, we treat all donors and patients as one system. So at the beginning, no donor is matched to any patient. Then, we start improving the matches step by step by checking compatibility. So if we find a better pairing, we update the current matches. We continue this process again and again until no better matches can be found. So, in the end, we get a set of matches that is already effective and acceptable for the given situation. So, and that's how iterative improvement works.
So our problem is with the exchange. So there are groups of patients who need a transplant and their family are willing to donate, but they are not biologically compatible. Like for example, they don't have the same blood type. There are some hospital or cases that they treat its incompatibility as a terminal failure, leaving patients to wait, and it even takes a year for a deceased donor. However, by viewing these families as a collective kidney exchange network, the hospital can overcome this biologically mismatch through chain donation. Given that, for example, donor A is not compatible with patient A, donor A might provide a kidney to patient B and donor B might provide a kidney to patient A, and so on. This transforms a series of individual dead ends into a coordinated, life-saving web that maximizes the total number of transplanted and ensures that no viable donor is wasted.
Now, let's take a look at the program code. First, we are going to define the compatibility table. So this is a dictionary where each donor is linked to the list of patients they are medically compatible with. We have donor A to patient 2 and patient 3, donor B to patient 1 and patient 3, donor C to patient 2 and patient 4, and last, donor D to patient 1 and patient 3. Now we have this function, augment. So this function is the core of our algorithm. It checks each compatible patient for a given donor. Now, if the patient is not yet visited, it marks them as visited to avoid infinite loops. Then if the patient is free, it assigns the donors directly. But if the patient is already taken, it tries to reroute the existing donor somewhere else. And that rerouting is what makes this iterative improvement. And if the new path is found, it updates both matching dictionaries and returns true. Pakikat na lang po kasi ang aking mouse nagloloko. Then we have this function. So this starts with everyone unmatched, then loops through each donor one by one. It calls the try-augment function to build the matching step by step. Mag-scroll ka! We also have the display compatibility, which prints the compatibility table as a start so we can see the initial state clearly, and display results, which prints the final match pairs and the summary at the end.
Now let us examine the results of our implementation of the Iterative Improvement Algorithm using the augmenting path approach. So as we can see here, the algorithm successfully produced a maximum matching of 4 donor-patient pairs, so which means that all donors were matched with compatible patients and no patient was left unmatched. This shows that the algorithm was able to fully utilize all available compatibility relationships in the system. So one of the key strengths of this approach is its ability to improve earlier decisions. During the process, some initial matches were rerouted to allow better overall pairings. Because of this, the algorithm avoided poor intermediate results and continued improving toward a better solution. In our scenario, the iterative improvement method was able to achieve the optimal result, since 4 matches is the maximum possible given the number of donors and patients. However, in general, this method may risk settling at a local optimum, especially if it does not explore alternative paths. In our case, this limitation was minimized or reduced through the use of augmenting paths, which allowed the algorithm to keep searching for better matches until no further improvement was possible. So because of its efficiency and ability to refine solutions, iterative improvement is recommended for solving this type of problem at scale, particularly in real-world applications like kidney exchange systems, where maximizing matches is essential. And overall, this study shows how algorithmic approaches can transform complex problems into effective and life-impacting solutions. So thank you for watching. Bye-bye.